What's up, guys? I'm Todd Davies, and this is a lecture on probability for the SYMSYS 1 Minds and Machines lecture series. This is an outline of the lecture today. I'm going to be talking about theoretical probability, the basic theory, conditional probability, and independence to start out. Then the different philosophical interpretations, so-called foundations of probability. We're going to take one of those interpretations and deepen it a bit and ask, how do we elicit probabilities from human probability judges, as we'll call them, and then do a survey of a particular set of findings about human probability judgment that is known as the Heuristics and Biases tradition of research. It comes mostly out of psychology and also behavioral economics and organizational behavior. So why should we study probability, especially in the context of a course on minds and machines? An important reason is because the theory of probability is used heavily as a way of understanding the human mind. In contemporary cognitive science and psychology, probabilistic models are very common, and they're getting increasingly sophisticated. So an understanding of the basic theory is important for that. Probability theory is also the foundation for modern statistics. And with the importance of data in our world, data collected through the internet and other means, understanding the deepest foundations of data analysis is very important and often a prerequisite for higher study in statistics. And finally, probability theory, in my experience, I was actually a statistics major in college, and I think the experience of many other students changes the way you think about the world. When you start seeing things in probabilistic terms, you become more sensitive to uncertainty and the evidence that affects our knowledge about the world. So we'll start with an overview of the basic theory. I'm going to present axiomatic probability theory in a classical formulation, more or less, that is less than 100 years old. So the axiomatic theory dates from the late 20s, early 30s. Kolmogorov in particular. There was an earlier development by Pierre-Simon Laplace in the early 19th century, and the laws of chance have been known for much longer than that, to gamblers especially. But the formal theory took a while to get going within mathematics. It's surprisingly recent. But it's also very accessible, and all you really need to understand it is some familiarity with set theory. The first definition I want to lay out here is for what we call a sample space. So we're going to let S, the capital S, be a set of possible outcomes, little s1, s2, up to sn, so n possible outcomes in this context C. And we're going to say that this large S is in this case, finite sample space for the context C, if and only if exactly one outcome among the elements of S is or will be true in C. So here's an example. Let the context be the particular flipping of a coin. Then we can say, as one possible sample space, that S equals the set heads, tails. That is a sample space for the context. Another possible sample space for this same act of flipping the coin is S prime, which I've defined as the set heads is observed, or tails is observed, or we cannot observe whether the coin is heads or tails. And yet another sample space is S double prime. Heads is observed and someone coughs. Heads is observed and no one coughs. Tails is observed whether someone coughs or not. So you can see that we construct the sample space in a way that suits our purposes. and any given action can be described, its outcomes can be described in multiple ways as different sample spaces. But once we set the sample space, then that will determine how we apply probability to that set of outcomes. Next, we're going to define the concept of an event space relative to our capital S sample space. And the event space we're going to denote with this capital E, which is a non-empty subset of the power set of S. The power set of S is just the set of all subsets of S. And we'll say in particular that capital E is an event space, also known as an algebra of events, on the sample space S, if and only if for every pair A and B of events in the event space, two conditions hold. First, if we take our sample space and remove event A, and this would also apply to B, but we'll just go with A for now, since they're arbitrarily assigned. And we define that as the complement of the set or event A complement. If that's that is an element of the event space. So the S complement of event A is in E. And point B, the union of events A and B is also in the event space. In particular, we call the elements of E consisting of single elements of S atomic events. So an example of an event space is as follows. If S is our sample space, and we'll say that's heads and tails in this case, then the event space is, and this shows the power set. It's the null set, the set heads and tails. Those are the two atomic events, and the set heads, comma tails, meaning in this case could be either heads or tails. So that set E is an event space on the sample space S. We can now define a probability measure. We're going to let capital S be our sample space and capital E be an event space on S. Then we can define a function capital P, which takes the event space into the unit interval from 0 to 1. And that function is going to be a parenthetically finitely additive probability measure on event space E, if and only if for every pair of events A and B in the event space, we have the following two conditions that hold. So first, the probability function applied to the entire sample space is defined to be 1. And secondly, if the intersection between events A and B is empty, in which case we say that A and B are disjoint events, and that's illustrated here. A and B in this diagram are subsets, are events within the total sample space. Then it's going to be the case that the probability function applied to the union of events A with B is equal to the sum of the probability of A plus the probability of B. And that's an additivity condition. And we'll say that the triple sample space, event space probability measure is a probability space, and it's finitely additive. So there's some basic corollaries that I want to go through that follow from this definition of the probability measure. It's a surprisingly rich theory. First, we have binary complementarity. So this says simply that if we have a probability space, SEP, and it's finitely additive, then for all events A and B that are in the event space, the probability of A complement, which in logic we would say the probability of not A, is simply equal to the probability, or 1 minus the probability of A. So that's the kind of complementarity in probability measure for the complementarity of the sets. And I'm going to go ahead and walk through this proof. I'm not going to do that for most of the proofs that are on here, but just to give you an idea of how they go, and then for the most part I'll let you read the proofs on your own. So the proof of this is the union of A with its complement is, of course, the entire sample space S by the definition of complementarity from set theory. Therefore, the probability of the union of A with its complement equals 1, since the probability of S equals 1 by the definition that we gave earlier of a probability measure. A and A complement are disjoint by the definition of complementarity. So by definition 1.5 part B, the probability of A union A complement is equal to the probability of A plus the probability of A complement. So probability of A plus the probability of A complement is equal to 1, and the result follows by subtracting the probability of A from both sides of the equation. So graphically, the way to think about this is that if we have a set like A, which is an event in this space, and S is the whole sample space, then its complement is just the negation of A, and the measure applied to all of this shaded area outside of the darker shaded area A is equal to 1, which is the measure for the whole rectangle, minus the measure applied to A. Second corollary says simply that the probability function applied to the null set is going to be 0. And in some formulations of probability theory that appears in the definition, here we can derive it from the definition that we gave earlier, and I'll let you read the proof. It's very simple on your own. Here's another corollary that's more involved, and therefore I'm not going to go through the proof here, but the principle tells us that if we have two events A and B and they are not disjoint, or we can't assume that they are disjoint, then the probability applied to the union is equal to, in this case, the probability of A plus the probability of B minus the probability of the intersection of A and B. So I can show this graphically using a Venn diagram. This is just the same corollary that we just talked about. In particular, I'm going to use it to show that the probability of the union of events A and B is equal to probability of A plus probability of B minus the intersection. And we can see that here by noting that the union is this whole set here, not drawing it exactly correct, and that we could get the measure of that, that is kind of the size of these two circles or ovals, by adding them together, and then just because when we do that, we're going to be adding in this part twice, we're going to just subtract that out once, and then we'll get the correct size, the correct measure for this particular area. The next corollary is what we're going to call the conjunction rule. And this will be useful later on as we talk about the psychology. We're going to say that for a probability space, for every pair of events, the intersection or the conjunction of the two events has to have a probability that's less than or equal to, can't be greater than, the probability of one of the conjuncts or one of the events in the intersection. So this I think we can see by just noting that the intersection here has to be smaller in measure, smaller in size, than either of the two events that are being intersected. That's all that rule says. We can then formulate another rule, which I'm going to call the disjunction rule, which is a version of what I just said for conjunction applied to the disjunction operator or the OR operator in logic. This simply says that the probability of event A union B or A or B has to be greater than or equal to the probability of one of the disjuncts. And here I'm going to leave this as an exercise to you to prove that proposition. It's also a corollary of the definition of probability. So since you've seen how the proof goes for the conjunction rule, you should be able to prove the disjunction rule on your own to check your understanding. We're now going to move to conditional probability, the second part of the lecture. We define conditional probability, which is written here as the probability of A given B. This vertical line is read as given. The probability of A given B of an event A for an event A given event B is defined as the probability of A intersect B divided by the probability of B, or the probability of A and B divided by the probability of B. So the way to think about this is we're conditioning, in this case on event B, we're saying let's stipulate that we're in this space, that event B has happened. Now, given that we know that, that becomes our full set sample space. So we can reset, we can renormalize and say, we know for sure, probability 1, that we're in event B. What is the probability of A given that we're in event B? And that is this area, the intersection, divided by the total. And there's a corollary to this, which is, the proof is so simple I didn't even give it, that provides a way of translating the probability of A and B, or the probability of A intersect B, into probability of A given B times probability of B. Now we're ready to prove probably the most important theorem in probability theory, certainly very influential theorem and very important for the study of minds and machines. It's known as Bayes' theorem, after the Reverend Bayes, who, even though axiomatic probability theory in its modern sense dates from the 20th century, this was proven in the early 19th century by Thomas Bayes. So the theorem says that for any pair of events A and B, and we're now assuming that we're in a probability space, the probability of A given B is equal to, and then there's a numerator term and a denominator term. The numerator says the probability of B given A times the probability of A. I'm going to divide that by the probability of B. And sometimes this probability in particular is expanded out as a sum of different disjoint, or a sum of different probabilities in a disjunction. to make up the full set B that we're conditioning on. For example, A and B plus the probability of A and B plus the probability of not A and B, that's equivalent to probability of B. So I've omitted that, but that can be done and is often useful in practice. So I'm going to go ahead and walk through this proof since it's such an important theorem. By our definition of conditional probability, we have that the probability of A given B is equal to probability of A and B divided by the probability of B. From set theory, we know that intersection is commutative, so A intersect B is the same as B intersect A. So the probability of A and B is equal to the probability of B and A. From our little corollary, the probability of B and A is equal to the probability of B given A times the probability of A. We can apply the corollary again to get probability of B and A is equal to its commutation probability of A and B, and that is equal to the probability of A given B times probability of B. So therefore we have, since these are the same, we have this equation, probability of A given B times probability of B equals probability of B given A times probability of A. And the theorem follows if we divide this equation by probability of B. Then we just get this formula here. So we've proven Bayes' theorem. Here's an example that applies the theorem to medical diagnosis. This comes from the physician and scholar David Eddy. He calculates the probability that a breast lesion is cancerous based on a positive mammogram. So first he estimates that the probability that a lesion will be detected through a mammogram, given that the mammogram, or given that the lesion is there, is about 0.792. So therefore the test will turn up negative when cancer is actually present about 20.8% of the time, 0.208% of the time, just 1 minus 0.792. When no cancer is present, the test produces a positive test result 9.6% of the time and is therefore correctly negative 90.4% of the time. So this 9.6% is what's known as a false positive rate. No cancer, but a positive result. The prior probability that a patient who has a mammogram will actually have cancer, this is known as the base rate or the prior, is taken to be, for this example, 1%. That's apparently an approximately accurate figure. So therefore, applying Bayes' theorem, the probability of cancer, given that we have a positive test result, positive mammogram, is this formula here, and I'll let you work through it on your own. And when we add all that up, we see that the patient with a positive test has less than an 8% chance of actually having breast cancer. So my question to you is, does that seem low to you? Most people, when they hear there's a positive test, and that in particular that probability that the lesion will be detected through a mammogram is almost 80%, will think that means they have cancer. But because the base rate is so low, it's only 1%, the probability that that gives for a particular person having cancer, given that they have a positive test result, is actually pretty low. It's only 8%, much higher than the 1% base rate, but not a particularly high percentage. Next, we're going to talk about independence. We can define independence of events and of events conditionally in probability theory, so we'll do both of those. This definition says that two events, A and B, are independent if and only if the probability of A and B, I'm now reading the intersection as the AND operator, is equal to the probability of A times the probability of B. So this is just a condition which might or might not hold for the probabilities of two events. When it does hold, then we say that they're independent. And that allows us to prove a little corollary, which provides a little more useful way of understanding, interpreting independence. Corollary tells us that events A and B, that if they're both have probabilities greater than 0, are independent if and only if the probability of A given B is the same as the probability of A. In other words, knowing that B has occurred tells you nothing about whether event A has occurred. That means that the events are independent, assuming that probability of B is greater than 0, and the same thing applies to probability of B. So knowing that A has occurred tells you nothing about whether B has occurred. So those are independent events, and the proof is here. I'll let you go through it on your own. So we can see independence in action if we consider consecutive flips of a coin, and we're going to assume it's a fair coin. We're going to let event A mean the event of heads happening on the first toss, and B be tails happening on the second toss. Probability for tails on the second toss is not affected by what happened on the first toss and vice versa. So our condition from the corollary for independence is fulfilled. If we assume that both sides of the coin have a non-zero probability of landing on top, then that means they're independent, and therefore probability of heads on the first toss and tails on the second toss is equal to the probability of heads on the first toss times probability of tails on the second toss. And if we assume the coin is unbiased, that means the probability of heads is equal to the probability of tails, 0.5. This means that probability for any sequence, in this case heads on the first toss, tails on the second toss, is 0.5 times 0.5 for two tosses. So that probability for that sequence is 0.25. And in fact, that's the probability for all of the possible sequences of two tosses: heads, 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 tails, tails, heads, and tails, tails. You can now consider the rolls of dice. Rolls of two die are often also usually considered to be independent of each other. If we have die with 6 sides, which are rolled simultaneously, the question that I'm posing to you as an exercise is, what is the probability that the sum of the two dice is 7? And applying the probability theory that you've learned so far, together with this independence assumption, you should be able to calculate the exact probability that a roll of two die will result in a sum that is exactly 7. We can also define independence for conditioned on an event. We say that two events A and B are conditionally independent given event C, if and only if it's the case that the probability of the intersection A and B given C is equal to the probability of A given C times the probability of B given C. And we can then prove, although I'm going to leave it to you as an exercise, the following propositions: that two events A and B are conditionally independent given event C, if and only if it's the case that either the probability of B given C equals 0, or the probability of A given B and C is equal to the probability of A given C. So what this says is that if probability of B given C is non-zero, then knowing that event B has happened, given that event C has happened, tells you nothing about the probability of A. And for an exercise, I'm going to suggest that you try to prove proposition 3.6 to test your understanding. Next, we're going to move to the foundations of probability, the philosophical interpretation of what probability means, and in what set of circumstances we can apply it. So foundations of probability is a very important topic because our interpretation of what probability means and when it's meaningful affects when we're willing to apply it. And you'll see that in the three main schools that have developed for foundations of probability. So the first and I think oldest view, usually known as the classical view of probability, and due to Pierre-Simon Laplace, is based on observing symmetries in the world and dividing possibilities by a total number. So in this case, we can look at this coin. This is actually an ancient Roman coin, the two sides of it, the head side and the tail side, which has the head of Sulla, who is a Roman general in the BCE time period. And you can see it's kind of oddly shaped, which I chose to remind us that we might be uncertain about whether this is a completely fair coin, not completely round. Nonetheless, on the classical view, the coin has two sides, and by symmetry, the probability, if we assume that the two sides are symmetric or equal, then the probability for each side turning up on a toss is then 1 divided by 2. So we have a basis for applying probability in this case, given the classical view. There's another view, which is the frequentist view, and this is the view that's based on repeated empirical observations. In order to apply the frequentist view, we don't necessarily have to observe symmetry, but we have to have a repeatable experiment or multiple observations that will give us the basis for a proportion or frequency calculation. So in this case, we would toss the coin many times. We would observe the proportion of times that the coin comes up heads versus tails. And then, on the frequentist view, we could define the probability for each side as the observed frequency or proportion of that outcome out of the total number of tosses. So you can see how the frequentist view could lead to a different estimate of the probability for each side turning up on the coin than the classical view, because it's based on actual tosses, and if the coin is somehow not fair, if it's weighted in one direction for another, then over another, for example, then the actual probability of heads might be somewhat different from 0.5, might be higher, for example, if it's weighted towards heads, or lower if it's weighted towards tails. The last major view, and there are lots of variations and others that have been put forward, but these are the main three, is called the subjectivist view. The subjectivist view basically defines probability epistemically. It says that probability is a function of our knowledge or our belief, and that you can apply it even in situations in which you can't necessarily do repeated experiments and where there's no symmetry or prior reasoning basis for assigning probability. So in the subjectivist view, you just make a judgment of how likely you think it is for this coin to turn up heads versus tails, say on the next toss. It can be applied to an exact event, like the next time I flip this coin, I think the probability will be 0.5 or some other number. So probability on this view represents your relative degree of belief in one outcome relative to another. And that view is also sometimes called the Bayesian view, although it's somewhat different from the use of Bayesian to refer to reasoning that is consistent with Bayes' theorem. So I prefer the term subjectivist for that reason, to make clear that we're talking about the philosophical foundational view of probability rather than simply something that's consistent with Bayes' theorem. I think they do that because Bayes himself could be viewed as a subjectivist, or at least his theorem seems to be the basis for that. So subjective probability then gives rise to the question of how do we elicit probabilities from people if we believe that they in fact can give meaningful probability judgments that are consistent with the probability calculus that I have defined. That's the subject of this section. So there are kind of two main methods and then a sub-method that I will define. The first method is the numerical method. We simply ask the probability judge, the person, what do you believe is the probability that it will rain tomorrow? And the answer is usually in the form of something like, I would put the probability of rain tomorrow at, and then an estimate. If we're doing percentages, then it would be between 0 and 100% inclusive, or the unit interval 0 to 1. So that's direct numerical response, one possible method and maybe the most straightforward. However, it could be viewed as an undisciplined method in the sense that someone could give any number and it's not clear what it means. And in particular, it's not clear that you could necessarily compare across people their probability estimates. Another method which is not as precise in the sense that it doesn't give point estimates as easily as the numerical method, but has the advantage of putting probability in the context of betting or of people making choices that could have real consequences for them. This method is known as the choice method. And the basic formulation is we ask the judge, which of the following two events do you think is more probable? Either that will rain tomorrow, sometime where we are, or it will not rain tomorrow. So we'll assume that it'll do one of those two things. And depending on which option the person chooses, will determine that they'll think as a result or infer that the one that they chose is the one that they think is more likely. If we want to turn this into something that incentivizes people to answer truthfully or to give their best estimate of the probability or the relative likelihood in this case, we could turn it into a bet. We could say, please choose between receiving $50 if it rains tomorrow, or, and that's option one, or option two, receiving $50 if the arrow lands within a displayed probability range. And we could modify this wheel on the right to make the red area and the blue area relatively smaller or larger. So question is, are you going to win money if we use the probability wheel? And in this right arrow, it looks like you're going to win money about 65% of the time based on the amount of area that it takes up, but that could be adjusted. Another way that this can be done is to simply spin the wheel or spin the dial and note the position it lands on between 0 and 1. And so those are equivalent methods known as the probability wheel. That allows us to put probability judgment in the context of a bet, so it incentivizes people to tell us what they really think. We might ask for different methods of probability elicitation, say the numerical response method and the choice method, if they're equivalent to each other. If they are, then we would expect them to be what I'm going to call procedurally invariant. And we'll define that as procedural invariance for a confidence measure, which is just an elicited subjective probability D. We're going to say that D is procedurally invariant with respect to two procedures of elicitation, pi and pi prime, if and only if the inferred inequality relations greater than sub pi and greater than sub pi prime are such that for all events A and B, the judge's confidence under the pi relation is greater in A is greater than the confidence in B if and only if it's greater than if and only if confidence in A is greater than B under the pi prime inequality relation. So the two procedures have to be consistent in that sense. They have to be invariant. So we need for the numerical method then to be equivalent to the choice method. That's what procedural invariance says. We can then define calibration with respect to an individual's confidence function D. We can say that their confidence is perfectly calibrated if, and it should be if and only if, for all values x in the unit interval 0, 1, and for all events E, if their confidence in E is equal to x, then the observed probability of E has to be equal to x. So for values of x in particular, but in the half interval from 0.5 to 1, if the confidence in E is greater than the observed probability of E, in this case we would have to do something like observe the probability that those events actually turn out, then the judge is said to be overconfident. And if confidence in E is actually less than probability of E for all these events, then we'll say that the judge is underconfident. So confidence is something that we usually think of as a positive trait, attribute, but it becomes an issue when we apply it to probability judgment. The ideal probability judge in this formulation is neither underconfident nor overconfident, but simply perfectly calibrated. Lastly, I want to talk about heuristics and biases in human judgment. This is where we bring the psychological and experimental study of human probability judgment to bear on in relation to the theory of probability that we have laid out earlier. So a way that researchers set about doing this was to simply use the theory of probability to predict whether people's judgments, or to predict that people's judgments would be consistent with the theory. And this is an experiment in which that turned out to be the case. This is a test of the binary complementarity principle, which we defined earlier in a corollary in the first section. So a number of experiments that were reported in papers by Tversky and Kohler in 94, by Walston, Badescu, and Zwick in 92, show that subjects' confidence judgments generally obey corollary 1.6. That's the binary complementarity relationship. So that their confidence in the complement of A tends to be 1 minus their confidence, again, their subjective probability in A. And the Walston et al. Paper is reported by Tversky and Kohler as presenting subjects with 300 propositions concerning world history and geography. For example, the Monroe Doctrine was proclaimed before the Republican Party was founded, was one such proposition people are being asked to make assessments about. True and false complementary versions of each proposition were presented on different days. So this is all part of the quote from that paper by Tversky and Kohler. And the finding was that the average sum probability for propositions and their complements was 1.02, which is not significantly different from 1. So this looks like an affirmation that probability theory is a pretty good way of modeling people's judgments, at least when it comes to binary complementarity. In a famous paper by Amos Tversky, who is shown up here, and Daniel Kahneman down here, published in the journal Science in 1974. They argued that humans, in their judgments, often employ heuristics, rules of thumb, rather than the laws of probability itself when they're making judgments about uncertain prospects. And in particular, I want to talk about two heuristics that they defined. One is the heuristic of representativeness, in which an event A is judged to be more likely than event B in a context C if A is more representative of C than B is. So we'll keep that in mind and see some examples of how it plays out. Another heuristic is the availability heuristic, in which event A is judged to be more likely than event B in a given context if instances of A are easier to bring to mind than instances of B in this context C. So let's talk about another experiment. I'd mentioned the one about binary complementarity. So this was part of a famous series of experiments done in the early 80s. In this case, they're asking people to predict or say what they think is the most likely outcome of it in a tennis match. So Tversky and Kahneman had subjects evaluate the relative likelihoods that Bjorn Borg, who was then the most dominant male tennis player in the world, you might think of Novak Djokovic as the kind of contemporary equivalent. They asked people to evaluate the likelihoods of A, that Borg would win the final match at Wimbledon, B, that he would lose the first set of that final match, C, that he would lose the first set but win the match, and D, that he would win the first set but lose the match. So think for a minute about how you would rank events A through D by likelihood. Well, I'm going to show you what their results were. They found that if people ranked for 1 meaning most probable and 2 meaning second most probable, etc., then the average rankings for these events were 1.7 for A, 2.7 for B, 2.2 for C, and 3.5 for D. Therefore, the subjects on average ranked the conjunction of Borg losing the first set and winning the match as more likely than that he would lose the first set. But the problem is, this is a violation of the conjunction rule that we talked about earlier, where the probability of a conjunction of events cannot be greater than the probability of one of the conjuncts. So they call that the conjunction fallacy, and their explanation is that people rank likelihoods based on the representative heuristic, which makes the conjunction of Borg's losing the first set but winning the match more representative of Borg, more like something that you'd think he would do, than is the proposition that Borg loses the first set, since he usually didn't lose. Here's an example of another conjunction experiment from the same paper in 1982. Tversky and Kahneman had subjects look at the probability of occurrence of natural disasters. Half of their subjects evaluated a basic outcome, for example, a massive flood somewhere in North America in 1983 in which more than 1,000 people drowned. And the other half, so this is a between subjects design, evaluated a more detailed scenario leading to the same outcome. For example, an earthquake in California sometime in 1983 causing a flood in which more than 1,000 people drowned. So you can see that this event, the earthquake and the flood, is a conjunction of two events, one of which is the flood. And what they found was that the estimates of the conjunction were significantly higher than those for the flood. So this, once again, violates the conjunction rule that we derived earlier. The scenarios that include a cause-effect story then appear to be more plausible to these participants than those that lack a cause, even though the latter are extensionally more likely. So their explanation was that the causal story makes the conjunction easier to imagine, which is an aspect of the availability heuristic, that is, the ease with which instances of the event, in this case the conjunction, are brought to mind versus just one of the conjuncts. As an exercise, I would suggest that you go back to the disjunction rule that we talked about as proposition 1.10, in which I asked you to prove in exercise 1.11, and see if you can construct an example experiment in which you would expect subjects to violate the disjunction rule. So this is to test your understanding of how these experiments are designed and how they relate to the theory of probability. In talking about Bayes' theorem, so to get back to conditional probability, we might ask if human judgment in general is Bayesian. Tversky and Kahneman looked a lot at this question, as have others in the Heuristics and Biases tradition. It's been a highly studied question. But there's been a lot of follow-on study showing that the judgment procedures that people use often result in answers or behavior that are consistent with Bayes' theorem. So the answer of whether human judgment is Bayesian depends on the type of judgment or cognitive task that's being performed, and to a lesser extent on the identity of the judge, the individual differences between people. And for a more complete discussion of this, I'm going to refer you to the separate lecture in this series, Are People Bayesian Reasoners?, done by Mike Frank. Another set of experiments which really affirms an effect that I think had been noted for a much longer time before that is based on the fallacy known as the Gamblers Fallacy. So in that paper from Science in '74, Tversky and Kahneman found that subjects on average regard the sequence heads, tails, heads, tails, tails, heads of a fair coin to be more likely than the sequence heads, 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 tails, 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 even though both sequences are equally likely, as they're both 6 tosses long, and therefore they both have 0.5 to the 6th probability of happening. But this result, and the result that they're equally likely, follows from the generalized definition of event independence. People in general regard, for example, a heads toss as more likely after a long run of tails tosses than after a similar run of tails or a mixed run. And that tendency in particular has been called the Gamblers Fallacy. Tversky and Kahneman's explanation for this is that people expect sequences of tosses to be representative of the process that generates them. Heads, tails, heads, tails, tails, heads is rated more likely than heads, 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 tails, 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 because the first sequence is more typical of a fair coin toss sequence generally, in which heads and tails are not grouped such that all the heads precede all the tails, but rather heads and tails are intermingled. And just to note a little bit on this, the Gamblers Fallacy also appears in rhesus monkeys. So it's not just in human behavior that we've observed it. It's a fairly deep bias, and it's seen in all kinds of places. And we'll look at one application of it to judgments in basketball in a minute here. So other findings, people have a general belief in what's called the hot hand. Both expert and lay basketball observers perceive basketball players as being more likely to make a shot after a hit, that is to have 2 hits in a row, or a run of previous, or before, or after a run of previous hits, than after a miss, even when the data indicate that shots are independent events as defined in definition 3.1. And that's from a paper by Gilovich, Tversky, and Vallone. This paper and this finding have spurred a large follow-on literature in which there's been a lot of resistance to this idea that the hot hand doesn't exist. I think that wasn't quite the claim of the original paper. They weren't saying that the hot hand never exists in any sport, but just that when it doesn't appear to exist in the data, that is, when there aren't more than the statistically expected number of runs that you would get by chance, people still perceive it in the data. And that's kind of the flip side of the gambler's fallacy, in that people believe that basketball shots are not independent events. They're not random, and they're a function of skill rather than just chance. That belief leads them, because they expect it to be true, to see more a greater percentage of runs than you'd expect by chance, even though that's not what the data showed in that particular study. And there have been a number of other studies that have affirmed that result. Another finding has to do with calibration and confidence, like we mentioned earlier. Various studies have shown that people's probability judgments are not well calibrated, that their confidence is not well calibrated, and that on average people exhibit overconfidence by the criteria in definition 5.2. You can see an overview paper by Ulrich Hoffridge from 2004 to give more on that. In some contexts, people show underconfidence, and this is also a kind of disputed finding about how general it is, but I would say overall the evidence supports more evidence for overconfidence than for its opposite, or for perfect calibration, which is quite rare, except in people like weather forecasters for whom probability judgments are part of their job. Just because it's part of someone's job doesn't mean they're going to be perfectly calibrated, however. Finally, another finding by Fox and Lvov in 2000 showed what amount to belief reversals under different procedures for probability elicitation. They found that judgments were affected by the elicitation method in violation of the procedural invariance principle of definition 5.1, and that the choice and numerical method sometimes yield opposite results. That is, people will judge one event as more likely under the choice method, and the other event is more likely in a comparison of two under the numerical response method. So we might ask, what are we seeing when we look at these results in probability judgment, where people appear to be systematically giving biased or wrong answers to probability questions? An analogy that Tversky and Kahneman like to give, which I think is instructive for how we view this set of results generally about human judgment, is that they're kind of analogous to perceptual illusions, visual illusions, like the well-known Muller-Lyer illusion, which is illustrated here. In the Muller-Lyer illusion, most people see the top line in this figure as appearing to be longer than the bottom line. And usually the explanation for that is because we live in a world in which the top line looks more like something which is, say, further away from us, where the two arrows pointing in on the outside there might be the interior corner of a distant edge in a room, whereas in the bottom figure, it looks more like that line is kind of protruding outward toward us, and that the arrows pointing outward are the outer edge of something that is facing us. So if that were the case, then our perceptual system might adjust for the line leaving the same length on our retina by inferring that the top line is longer than the bottom line, and therefore seeing it that way in the illusion. So it's actually a useful thing for the visual system to do this, but it leads us astray in this particular example where it's just a two-dimensional figure. If we overlay a frame on this which allows us to see that, in fact, the lines are the same length, or you might even say that the bottom line is a little longer, we don't have trouble in this framing seeing that the two lines are essentially the same length, as we get the right answer when we make it transparent in this way. And similarly, in the case of cognitive illusions, what researchers in the field have found is that when you give enough context and enough of a frame for people to see the right answer to a probability judgment question, they tend to get it right. So the claim that there are cognitive illusions is analogously to perceptual illusions, not a claim that people's judgment is bad, but rather that the illusions reveal something about how the mind works and how it's adapted for contexts of probability judgment in which it sometimes gets the wrong answer. Work on probability in human judgment and cognition has proceeded in various directions, and I just want to mention a few perspectives that have emerged since the classical work of Heuristic and Kahneman, which began in the late 1960s and lasted through about the mid-90s. So Danny Kahneman went on to win the Nobel Prize in economics for the joint work with Tversky. He won that in 2002, and tragically, Tversky was killed in 1996, so he didn't share in the prize. But in the later work, Kahneman with Shane Frederick applied earlier work by Stanovic and West to argue that human judgment can be characterized as broadly occurring in two different systems in the mind and brain. A system one, which they characterize as being quick and intuitive, in which judgments are kind of automatic. And they believe that the heuristics and biases that are observed in most of their experiments are a result of system one doing its work. They contrast that with system two, which is said to be a slower, more deliberative, and more hard rule governed system in which we're more likely to get the right answer. This is the kind of thinking we're doing when we do a mathematics problem and we get it right. So there's been a lot of interest in this dual process model growing out of the heuristics and biases tradition. Some of the results in heuristics and biases have been reinterpreted by different schools of researchers. One such is known as evolutionary psychology. For example, Gerd Gigerenzer and Peter Todd, who wrote a major book about applying evolutionary psychology to the study of judgment in the late 90s, and this work continues. That work tends to argue that human cognition, behavior, the way the brain and mind work have evolved for the particular environment that we are in, and that they have adapted well to that environment. And so if you want to understand why people do what they do, why they make judgments like they do, then you have to understand that environment, and then you will see that behavior and cognition are more adaptive than they might seem if you just look at these laboratory experiments. I think this was partly a response to the possible interpretation of the heuristics and bias literature, which is that people are just irrational or are not well adapted to our environment. The evolutionary psychologists have tried to construct arguments that the heuristics that we use are in fact adaptive most of the time and make good sense. That is, that they are what is sometimes called boundedly rational. There's also a school of thought, I think originally due to John Anderson, but popularized in the area of judgment and decision-making by Oxford and Chater, and that's known as the rational analysis of cognition. This is a methodological approach that tries to make predictions, much as the early heuristics and biases researchers did about what people will do based on the theory of probability and or decision theory or logic, and then tries to see how well that predicts human behavior. And when it doesn't seem to, the rational analysis tradition generally seeks an explanation that tries to reconcile human behavior with some idea of rationality before deciding that people are just irrational. So this can often mean reinterpreting subjects' responses so that what people are doing makes sense after all, or would make sense in most circumstances, or is answering a question that people are more likely to face in the real world than the one that they're being asked in the lab, and that people shouldn't be necessarily held to blame if they don't get the answer right to a math problem, basically. So that's part of the, I think, what is kind of an ongoing debate and working out of in what circumstances probability is a good model or not for human judgment. And the work has gotten more sophisticated, I think, especially when it comes to computational modeling for tasks like learning and language, categorization, perception, and the basic processes of the brain. In the application of probabilistic and Bayesian models to cognition using computation. And an example would be the work of Josh Tenenbaum and colleagues, which includes Noah Goodman, who's a faculty member here at Stanford, and also I think a number of other faculty would be in this tradition, have studied with Tenenbaum or Goodman. Anyway, this is an exciting area of research. I think there is a lot to be said about the relationship between probability theory and human thinking, and probability and the use of data and statistics. And I hope today's lecture has given you a good foundation for learning more about all of that.